Okay, so let's get started. I'm going to kind of redo deep learning a little bit. So because I think you need to essentially take this 3-month long course by Google's engineers in Udacity, which is free, but we don't have 3 months. So I basically reran through this course. I went into it in 2016. Most of it is enough for us. Um, and Siva and I, when we were taught this course in New Zealand, we did this. Um, so now I'm going to give you a full-blown quick compression of this 3-month long course, and it preps you to do TensorFlow and everything. But we have the minimal concepts we need to move on with other things. So here is the link to the course. It's you know, it's right here. It's free. It's done by Google's engineers, and that's how I learned this stuff. So then you have this is a nice website. It's a really good resource. So if you want to sort of have a quick read through things while this is a quick intro to it. Of course, this is the book. I have the hard copy here from Combion's library. This is really what you want. It's like our Kevin Murphy's book, but for deep learning. It's really good. And you can get the free PDF from Cornell anyway. Okay, we've already seen deep learning. People talk about it, artificial intelligence. Okay, so it can be used for both supervised learning, where you have training data with known labels, for example, regression or classification, or you can also use it for unsupervised models. We will get to the end of today for Fika, hopefully, this video on autoencoders. Or there's no rush. You can take it easy. We have time. So this also allows you to do unsupervised modeling, unsupervised models. Okay, the downsides or plus sides maybe are you need lots and lots of data to train a very, very good deep learning model. Its biggest advantages are you can do online learning, so you can update new data that comes in with known labels. It uses this very nice trick called backpropagation, which we saw in a kind of a hurry last time. I'll do it more slowly now. And then it can use this standard heuristic local optimization, stochastic gradient descent. There are some more interesting regularization tricks to control the complexity of the model, called dropout and things like this. So we'll see these concepts. So initially, the outline is something like this. Okay, this is literally like 3 months into 50 minutes. So we'll first get into fully connected network, really understand it, recall logistic regression and things like this. Then we'll get into what I was about to cover last time, which is convolutional neural networks. This is ideal for classifying images. And then we will get into the ideas for recurrent neural networks, which we really need for text and speech processing. Again, concepts directly from these guys. So Arpan and Vincent. So most of the videos I'll show are Vincent's videos, so Google guys. And then I'll show the basic idea behind an autoencoder again, one of these simple videos. That's enough conceptually, and of course I have links to various preprints in the archive if you want to really chase the details. But that is minimally what we need to be able to progress further with all the extended code from Adam Brendel's bag. Okay, so that's with Keras and TensorFlow as well. Okay, so this should only take 46 seconds. So let's recap linear regression.
Let's get started training a logistic classifier. The logistic classifier is what's called a linear classifier. It takes the input, for example, the pixels in an image, and applies a linear function to them to generate its predictions. A linear function is just a giant matrix multiply. It takes all the inputs as a big vector that will denote x, and multiplies them with a matrix to generate its predictions, one per output class. Throughout, we'll denote the inputs by x, the weights by w, and the bias term by b. The weights of that matrix and the bias is where the machine learning comes in. We're going to train that model. That means we're going to try to find the values for the weights and bias which are good at performing those predictions. How are we going to use those scores to perform the classification? Well, let's recap our task. Each image that we have as an input can have one and only one possible label. So we're going to turn those scores into probabilities. We're going to want the probability of the correct class to be very close to 1, and the probability for every other class to be close to 0. The way to turn scores into probabilities is to use the softmax function, which I'll denote here by S. This is what it looks like. But beyond the formula, what's important to know about it is that it can take any kind of scores and turn them into proper probabilities. Proper probabilities sum to 1, and they will be large when the scores are large, and small when the scores are comparatively smaller. Scores, in the context of logistic regression, are often also called logits.
Okay. So it's a lot of new words, right? But it's basically what we saw for linear regression, except for logistic regression, we need to predict outcomes. So the pre-final layer, we're going to have scores for each of the, say, k classes, and then we need to somehow decide which one it is. So for that, we just use the softmax layer on the outside.
Have you heard about fuzzy techniques?
Yeah, I actually published a paper, went to a fuzzy conference in 2013. Yeah, I know a little bit about it. I mostly work on the arithmetic end of the fuzzy guys, because interval arithmetic essentially can be used for fuzzy logic and fuzzy methods. But, you know, it's not, well, it's definitely not used right now for whatever. Yeah. It's a different community. Yeah.
Because I work too with fuzzy classifications.
Yeah.
So you can probably use.
Yeah. I mean, mathematically speaking, it's sensible, but I think the community itself is quite small. You know, a very small community relative to people that do non-fuzzy set theory. So, yeah. So anyway, let's take that over here. It's okay. So this is just, you know, you guys know this is regression, and this is in fact what we were trying to simulate over x1 and x2 last time over a plane with some random noise. So we have our sort of general model, y equals mx plus c. So we will revisit this equation when we finish this module. So again, we saw this. Another way to look at a linear model is simply this, x1, x2, x3 multiplied by weights added up. Basically gives you a linear model. This was the first image in Adam's intro, which I think is good, but he does assume that you already know a little bit of data science and machine learning. So now let's watch this. I mainly, it's important because there are new concepts here which we haven't seen.
Okay, so now we have all the pieces of a puzzle. The question, of course.
Sorry. I don't want to transit directly from my link to Oregon, you know. There we go.
Okay, so now we have all the pieces of a puzzle. The question, of course, is how we're going to find those weights W and those biases B that will get our classifier to do what we want it to do. That is, have a low distance for the correct class, but have a high distance for the incorrect class. One thing you can do is measure that distance averaged over the entire training set for all the inputs and all the labels that you have available. That's called the training loss. This loss, which is the average cross entropy over your entire training set, is one humongous function. Every example in your training set gets multiplied by this one big matrix W, and then they get all added up in one big sum. We want all the distances to be small, which would mean we're doing a good job at classifying every example in the training data. So we want the loss to be small. The loss is a function of the weights and the biases. So we're simply going to try and minimize that function. Imagine that the loss is a function of two weights, weight 1 and weight 2, just for the sake of argument. It's going to be a function which will be large in some areas and small in others. We're going to try to find the weights which cause this loss to be the smallest. We've just turned the machine learning problem into one of numerical optimization. And there's lots of ways to solve a numerical optimization problem. The simplest way is one you've probably encountered before, gradient descent. Take the derivative of your loss with respect to your parameters and follow that derivative by taking a step backwards, and repeat until you get to the bottom. Gradient descent is relatively simple, especially when you have powerful numerical tools that compute the derivatives for you. Remember, I'm showing you the derivative for a function of just 2 parameters here. But for a typical problem, it could be a function of thousands, millions, or even billions of parameters.
Okay, so that's Siraj you saw, like he's very popular in the post-millennial generation. He raps math equations. I took one of his courses. Anyway, so yeah, it's not as good as 50 cents, you know. But, all right, let's. This is the main. So there was this thing called cross entropy. Just remember it. We'll formally revisit and understand it soonish. Okay, when we go back. So now, what is stochastic gradient descent? Again,
the problem with scaling gradient descent is simple. You need to compute this gradient. Here is another rule of thumb. If computing your loss takes n floating point operations, computing its gradient takes about 3 times that compute. As we saw earlier, this loss function is huge. It depends on every single element in your training set. That can be a lot of compute if your data set is big. And we want to be able to train on lots of data because in practice, on real problems, you'll always get more gains the more data you use. And because gradient descent is iterative, you have to do that for many steps. That means going through your data tens or hundreds of times. That's not good. So instead, we're going to cheat. Instead of computing the loss, we're going to compute an estimate of it. A very bad estimate. A terrible estimate, in fact. That estimate is going to be so bad, you might wonder why it works at all. And you would be right, because we're going to also have to spend some time making it less terrible. The estimate we're going to use is simply computing the average loss for a very small random fraction of the training data. Think between 1 and 1,000 training samples each time. I say random because it's very important. If the way you pick your samples isn't random enough, it no longer works at all. So we're going to take a very small sliver of the training data, compute the loss for that sample, compute the derivative for that sample, and pretend that that derivative is the right direction to use to do gradient descent. It is not at all the right direction. And in fact, at times, it might increase the real loss, not reduce it. But we're going to compensate by doing this many, many times, taking very, very small steps each time. So each step is a lot cheaper to compute, but we pay a price. We have to take many more smaller steps instead of one large step. On balance, though, we win by a lot. In fact, as you'll see in the assignments, doing this is vastly more efficient than doing gradient descent. This technique is called stochastic gradient descent and is at the core of deep learning. That's because stochastic gradient descent scales well with both data and model size, and we want both big data and big models. Stochastic gradient descent, SGD for short, is nice and scalable, but because it's fundamentally a pretty bad optimizer that happens to be the only one that's fast enough, it comes with a lot of issues in practice.
Okay, all these videos, I think, you know, if you want to get a job in machine learning and data science, whatever, I highly recommend just watching these videos or whatever, the bathtub or whatever you do. You don't need to do all the homework, but there's a lot of basic concepts. And Vincent does a very good job of Okay, so there are some more details, those who are into optimization, on how to do parallel stochastic gradient descent without locks. So I think this is one of the algorithms that's in TensorFlow. Okay, read those preprints. So now the next thing is, let's watch this.
That's the case in general. If you have n inputs and k outputs, you have n plus 1 times k parameters to use, not one more. The thing is, you might want to use many, many more parameters in practice. Also, it's linear. This means that the kind of interactions that you're capable of representing with that model is somewhat limited. For example, if two inputs interact in an additive way, your model can represent them well as a matrix multiply. But if two inputs interact in a way that the outcome depends on the product of the two, for example, you won't be able to model that efficiently with a linear model. Linear operations are really nice, though. Big matrix multiplies are exactly what GPUs were designed for. They're relatively cheap and very, very fast. Numerically, linear operations are very stable. You can show mathematically that small changes in the input can never yield big changes in the output. The derivatives are very nice too. The derivative of a linear function is constant. You can't get more stable numerically than a constant. So we would like to keep our parameters inside big linear functions, but we would also want the entire model to be nonlinear. We can't just keep multiplying our inputs by linear functions, because that's just equivalent to one big linear function. So we're going to have to introduce nonlinearities.
Yeah, so that's where the magic happens, right? So now we have these nonlinear activation layers. And so we kind of saw this, and a particular kind, is this ReLU we saw. So we could have a soft plus activation or this rectified linear unit. So now let's just dive into neural networks.
Because we're lazy engineers, we're going to take something that works, our logistic classifier, and do the minimal amount of change to make it nonlinear. We're going to construct our new function in the simplest.
So he meant when he said because we are lazy engineers, right? I mean, most of this is just art and engineering, really. It's pretty amazing. It's useful at all.
Way that we can think of. Instead of having a single matrix multiply as our classifier, we're going to insert a ReLU right in the middle. We now have two matrices, one going from the inputs to the ReLUs, and another one connecting the ReLUs to the classifier. We've solved two of our problems. Our function is now nonlinear, thanks to the ReLU in the middle, and we now have a new knob that we can tune, this number h, which corresponds to the number of ReLU units that we have in the classifier. We can make it as big as we want. Congratulations, you built your first neural network. You might ask, wait a minute, where's my neuron? In the past, when talking about neural networks, I remember seeing diagrams with dendrites, axons, activation functions, brains, neuroscience. Where is all that?
Yeah, anyway, that's history. Israelis are doing really amazing things, though, combining silica and yeah. I don't know any more about that literature. There is research in that direction. Yeah, so this is a pop quiz. Is decision tree, which you've seen before, a linear model? Says no. You guys agree? Mahmoud? Yes. You agree with him? Yeah. So that's good, yes. The answer is there in detail, but yeah, it is, right? Because you're chopping up, you're actually approximating simple functions, right? That's basically as nonlinear as it can get, right? That's the ingredient for measure theory. Okay, but of course, decision trees suck at some point, right?
But it's random forest.
Well, yeah, I mean, random forests are just, I don't know, jazzes of decision trees, right? So you have ensembles and things like this, but the basic idea of splitting in each coordinate at a particular value and making these axis parallel splits, the fundamental, what computer science, the data structures people will call what would they call it? Metric tree, right? A multi-dimensional metric data structure. This class of trees, it's in this big book called Foundations of Data Structures by Hansen. But the problem with this class of trees is that they're called space partitioning trees. So they actually partition space, right? The full hull of all the points. So when you partition space and the dimensions increase, right, you need to chop a lot to get to some little zoomed in area, right, if your data is highly concentrated. So there are limits to sort of classical decision trees. They're easy to interpret and so on, but they quickly reach limits, both scaling up to large data as well as the way in which they deal with, and there are other variants, but let's not go into it. Because you can have hyperplane split trees. So hyperplane split trees will basically, still tree-based structures, but they don't have the problem of space partitioning trees because they will have an arbitrary split of a hyperplane, which is, remember, the first ingredient of our neural network, right? You have the W's coming in. That's just a dot product operator with the simplest, if, on which side of the hyperplane. That is just a hyperplane. And this thing composes hyperplanes, the hyperplane split tree, splits the data, partitions it, and then it'll split the other half by another arbitrary hyperplane and so on. But the advantage of hyperplanes is they can zoom in quickly on where the action is, if you design the algorithms like that. And there are also other algorithms called ball trees, which will actually put a centroid where the data is, and then some radius around it. So you can put centroids close to clusters. And that's the heart of k-means algorithms. All the k-means stuff we've seen, they use these ball trees. They're also good at zooming in and can fight the curse of dimensionality. But what we're doing with deep learning, I'm answering this because there was a big debate in Combient data scientists about this exact topic. So what we're doing with deep learning, if you really look into it, is actually using a whole bunch of hyperplane split trees with nonlinear outputs coming out. So it's actually a very interesting composition of multiple hyperplane split trees, right? And it's hard to visualize what the hell is really going on. So like proper Lapnik-Chernyshkin theory and things like this, like MathStats, it's way behind what's happening in deep learning. So we don't know yet. I mean, it's a lot of money pumped in, especially by the US military, into this because they want to have systems they can understand. They call it explainable machine learning. Well, because they're shooting people in drones, whatever they do, right? Or make sure the combat soldiers that go in, whatever the machine tells them to do is actually has an explanation, right? So that's still an active research area now. Okay, we saw this input, hidden output. And we already kind of ran this in a hurry in Keras. I'll quickly march through that as we progress. So this is, again, the architecture is all-to-all or densely connected or fully connected because everything is connected to everything. You have multiple hidden layers, and we saw when it has more than a couple, it's called deep learning because it was quite deep to have the optimizations work in the 80s and so on. Okay, so what does it mean to go deep? What do each of the hidden layers learn? Right? So this, we need some intuition. So let's listen to Vincent.
So now you have a small neural network. It's not particularly deep, just 2 layers. You can make it bigger, more complex, by increasing the size of that hidden layer in the middle. But it turns out that increasing this H is not particularly efficient in general. You need to make it very, very big, and then it gets really hard to train. This is where the central idea of deep learning comes into play. Instead, you can also add more layers and make your model deeper. There are lots of good reasons to do that. One is parameter efficiency. You can typically get much more performance with fewer parameters by going deeper rather than wider. Another one is that a lot of natural phenomena that you might be interested in tend to have a hierarchical structure, which deep models naturally capture. If you look at a model for images, for example, and visualize what the model learns, you'll often find very simple things at the lowest layers, like lines or edges. Once you move up, you tend to see more complicated things like geometric shapes. Go further up, and you start seeing things like objects, faces. This is very powerful because the model structure matches the kind of abstractions that you might expect to see in your data. And as a result, the model has an easier time learning them.
And yeah, we will see this in our first convolutional neural net. Okay, so of course, f composed with g derivative is f derivatives composed with g multiplied by g's derivative, right? This is the chain rule. So let's sync this.
One reason to build this network by stacking simple operations like multiplications and sums and ReLUs on top of each other is that it makes the math very simple. Simple enough that a deep learning framework can manage it for you. The key mathematical insight is the chain rule. If you have two functions that get composed, that is, one is applied to the output of the other, then the chain rule tells you that you can compute the derivatives of that function simply by taking the product of the derivatives of the components. That's very powerful. As long as you know how to write the derivatives of your individual functions, there is a simple graphical way to combine them together and compute the derivative for the whole function. There's even better news for the computer scientist in you. There is a way to write this chain rule that is very efficient computationally, with lots of data reuse, and that looks like a very simple data pipeline.
Siraj is popping all the time, man. I haven't cleared my cookies, so. Okay, this is backpropagation. To properly understand this, you're going to minimally need 20 minutes or so. I sort of did this myself to re-understand this. As you know, I forget a lot and re-remember, but what I would do, I think it's important you understand this, especially if you're going to do a project in this stuff. Go here. This is a really nice Stack Exchange chat. Walk through this guy's answer. It's very delicate and nicely done in just a simple expression. Z equals x1 times x2 plus sine of x1. So you need to understand what's the forward pass, what's the reverse pass, symbolically, but with the example walk through. Now, of course, you want to understand this in a much higher dimensional context with different architectures. So for that, this is worthwhile watching. It's a long video. I won't show that now because we want to make Fika. Let's watch this 1 minute 54 second.
Here's an example. Imagine your network is a stack of simple operations, like linear transforms, ReLUs, whatever you want. Some have parameters, like the matrix transforms. Some don't, like the ReLUs. When you apply your data to some input x, you have data flowing through the stack up to your predictions y. To compute the derivatives, you create another graph that looks like this. The data in that new graph flows backwards through the network, gets combined using the chain rule that we saw before, and produces gradients. That graph can be derived completely automatically from the individual operations in your network. So most deep learning frameworks will just do it for you. This is called backpropagation, and it's a very powerful concept. It makes computing derivatives of complex functions very efficient, as long as the function is made up of simple blocks with simple derivatives. Running the model up to the predictions is often called the forward prop, and the model that goes backwards is called the back prop. So to recap, to run stochastic gradient descent, for every single little batch of your data in your training set, you're going to run the forward prop and then the back prop, and that will give you gradients for each of your weights in your model. Then you're going to apply those gradients with a learning rate to your original weight.
Sorry, guys. How do I turn off the subtitles like this?
The CC.
Jeez, I can't see anything. Because he's quite clear, right, with his, I guess, Belgian or French accent.
And update them. And you're going to repeat that all over again many, many times. This is how your entire model gets optimized. I'm not going to go.
So do you see there is a bug in the slide?
More of the math of what's going on in each of those blocks. Because again, you don't typically have to worry about that. And it's essentially the chain rule. But keep in mind this diagram. In particular, each block of the back prop often takes about twice the memory that's needed for the forward prop, and twice the compute. That's important when you want to size your model and fit it in memory, for example.
So, you saw there's a delta missing in the second update for W2, right? All right. How do you set the learning rate? So learning rate is our little alpha, like how jumpy things are. this is as Vincent pointed out, this is the art, because we're basically doing these drunken walks with these small random batch sizes. But then how, you have to do them many, many times. So you have to do small jumps, but if you keep on doing small jumps, that's also bad. So there is a whole art of, learning adaptively learning the learning rate. And so anyway, there are links to this. It's all heuristic and some conditions. I went to a seminar recently. Were you there at the probabilistic computing seminar by this German guy? He was actually really putting all of these, adaptive learning and stochastic gradient descent all in a very nice probabilistic computing framework with the Bayesian interpretation. And so anyway, at least in a single, non-distributed setting, they have like a kind of automatic way of learning the learning rate and things like this. But that's current research. I asked them if they can do it distributed. They said no, not yet. Okay, that's just like a very quick recap of a bunch of stuff you kind of know, but now we are on the same page. What we're going to now, move on to is not just these dense, fully connected layers, right? We want to start playing with the architecture itself of these edges. So the one interesting one is called the convolutional neural network. So this has been around for a while. And so here the idea is that, so these could be your, say, images, each pixel or whatever, input downstairs. And then you see you have these little wires that are sitting on this green guy, which is another node, one level further. And you see that this guy has 4 edges coming from these 4 x0, 0, x1, 0, x1, 1, and x0, 1, right? So basically, only this corner affects the weights that go here. Only this chunk affects the weights that go here, and so on. So it's not an all-to-all topology. It's a locally specified topology. So we will see this in more formally when we get into QS, but just bear that in mind. And let's see, watch this, and I'll see if Tilo's here.
Let's talk about convolutional networks, or convnets. Convnets are neural networks that share their parameters across space. Imagine you have an image. It can be represented as a flat pancake. It has a width, a height, and because you typically have red, green, and blue channels, it also has a depth. In this instance, depth is 3. That's your input. Now imagine taking a small patch of this image and running a tiny neural network on it with, say, k outputs. Let's represent those outputs vertically in a tiny column like this. Now let's slide that little neural network across the image without changing the weights. Just slide across and vertically like we're painting it with a brush. On the output, we've drawn another image. It's got a different width, a different height, and more importantly, it's got a different depth. Instead of just R, G, and B, now you have an output that's got many color channels, k of them. This operation is called a convolution. If your patch size were the size of the whole image, it would be no different than a regular layer of a neural network. But because we have this small patch instead, we have many fewer weights, and they are shared across space. A convnet is going to basically be a deep network where instead of having stacks of matrix multiply layers, we're going to have stacks of convolutions. The general idea is that they will form a pyramid. At the bottom, you have this big image but very shallow, just R, G, and B. You're going to apply convolutions that are going to progressively squeeze the spatial dimensions while increasing the depth, which corresponds roughly to the semantic complexity of your representation. At the top, you can put your classifier. You have a representation where all the spatial information has been squeezed out and only parameters that map to content of the image remain. So that's the general idea. If you're going to implement this, there are lots of little details to get right and a fair bit of lingo to get used to. You've met the concept of patch and depth. Patches are sometimes called kernels. each pancake in your stack is called a feature map. Here you're mapping 3 feature maps to k feature maps. Another term that you need to know is stride. It's the number of pixels that you're shifting each time you move your filter. Stride of 1 makes the output roughly the same size as the input. A stride of 2 means it's about half the size. I say roughly because it depends a bit about what you do at the edge of your image. Either you don't go past the edge, and it's often called valid padding as a shortcut, or you go off the edge and pad with zeros in such a way that the output map size is exactly the same size as the input map. That is often called same padding as a shortcut.
Okay, so padding, stride, what else? Patch size. These are all control parameters in Keras. I figured this will be way faster than me trying to do an animation, and it's not going to work, right? The Google team is loaded. And you know, this is something I strongly recommend if you look into Udacity and stuff. Facebook has a whole lot of stuff as well. Why are they, Facebook and Google, releasing, you know, excellent videos and courses that you can do certifications and so on? Because they want people to do this stuff. It's a big supply-demand problem, right? So here are the papers that I would read. NIPS papers by Jeffrey Hinton, who's like a superstar guy now. Everyone talks about him. So he's the main guy behind a lot of these ideas. Here is your, you know, an interesting blog about it. It's a bit old. Recurrent neural networks are something else. We will, and especially we will do a long short-term memory variant of the recurrent neural network. So here the idea is that you know, we want to somehow remember, you know, somehow a feedback loop, or if you're reading a sentence or watching a movie or whatever, something that has a natural time structure to it, we want to be able to learn from the recent events, right? It's you know, it's kind of like a higher order Markov chain, but so this is the other important RNNs.
We've already seen how a convolutional network uses shared parameters across space to extract patterns over an image. Now you're going to do the same thing, but over time instead of space. This is the idea behind recurrent neural networks. Imagine that you have a sequence of events. At each point in time, you want to make a decision about what's happened so far in the sequence. Imagine that you have a sequence of events. At each point in time, you want to make a decision about what's happened so far in the sequence. If your sequence is reasonably stationary, you can use the same classifier at each point in time. That simplifies things a lot already. But since this is a sequence, you also want to take into account the past, everything that happened before that point. One natural thing to do here is to use the state of the previous classifier as a summary of what happened before, recursively. Now, you would need a very deep neural network to remember far in the past. Imagine that this sequence could have hundreds, thousands of steps. It would basically mean to have a deep network with hundreds or thousands of layers. But instead, we're going to use tying again and have a single model responsible for summarizing the past and providing that information to your classifier. What you end up with is a network with a relatively simple repeating pattern, with part of your classifier connecting to the input at each time step, and another part called the recurrent connection connecting you to the past at each step.
Okay. Yeah, this is really good to watch as well. But let's. So yeah, if you so what we will be using often is this pattern called long short-term memory, which is a certain kind of recurrent neural network. And remember, Vincent mentioned the word tying. You guys know what it is? Good. It just means that we, you know, when we're doing convolutional neural net, we were moving around the stuff, but we fixed the parameters to be the same for that, you know, so that the weights are the same across the whole convolution, this whole sweep, right? So, but then you will do another sweep to get us a different you know, a different channel, right? That's the depth of the convolutional neural net, right? So for each channel, the weights are fixed. And that's what he means by tying. It's the same way with RNN, you know, RNNs. You have this weight parameter that gets fixed across. So that's why he removed the indices, right? But if you watched all the videos, you will get all that. So yeah, this is essentially the architecture of the following video is what I would watch. The one thing I really want to get into you guys is autoencoder, which is now very different. Oh, by the way, there is I should say that CNNs are already old. Okay, so you know this is just to say this is some much newer thing Hinton's done in the last couple of years or less. It's called the capsule networks. I strongly recommend reading this, especially if you want to do well in an interview of some smart-ass guy who's read a lot of blogs about what's happening in deep learning. This will be probably a question easily in 2018, right? So this is a different architecture, the different ways in which you're multiplying. The main drawback is it's sort of explained in this one picture. CNNs, convolutional neural nets, because they're sweeping like this, they will not be able to distinguish between this as a face and this as a face. This is not the face, it has all the parts of a face. So capsule networks at a very high level fixes this by encoding spatial relationships into the architecture itself. So let's I'm not going to really get into that in the rest of the code here, but okay, so last video before Fika is autoencoder. So remember, this is the problem of unsupervised learning, and I think I'll pour the hot water. You guys watch this. Unfortunately, this is commercial.
There are times when it's extremely useful to figure out the underlying structure of a data set. Having access to the most important data features gives you a lot of flexibility when you start applying labels. Autoencoders are an important family of neural networks that are well suited for this task. Let's take a look. In a previous video, we looked at the restricted Boltzmann machine, which is a very popular example of an autoencoder. But there are other types of autoencoders like denoising and contractive, just to name a few. Just like an RBM, an autoencoder is a neural net that takes a set of typically unlabeled inputs and, after encoding them, tries to reconstruct them as accurately as possible. As a result of this, the net must decide which of the data features are the most important, essentially acting as a feature extraction engine. Autoencoders are typically very shallow and are usually comprised of an input layer, an output layer, and a hidden layer. An RBM is an example of an autoencoder with only 2 layers. Here's a forward pass that ends with a reconstruction of the input. There are 2 steps, the encoding and the decoding. Typically, the same weights that are used to encode a feature in the hidden layer are used to reconstruct an image in the output layer. Autoencoders are trained with backpropagation using a metric called loss. As opposed to cost, loss measures the amount of information that was lost when the net tried to reconstruct the input. A net with a small loss value would produce reconstructions that look very similar to the originals. Not all of these nets are shallow. In fact, deep autoencoders are extremely useful tools for dimensionality reduction. Consider an image containing a 28 by 28 grid of pixels. A neural net would need to process over 750 input values for just one image. Doing this across millions of images would waste significant amounts of memory and processing time. A deep autoencoder would encode this image into an impressive 30 numbers and still maintain information about the key image features. When decoding the output, the net acts like a two-way translator. In this example, a well-trained net could translate these 30 encoded numbers back into a reconstruction that looks similar to the original image. Certain types of nets also introduce random noise to the encoding-decoding process, which has been shown to improve the robustness of the resulting patterns. Have you ever needed to use an autoencoder to reduce the dimensionality of your data? If so, please comment and share your experiences. Deep autoencoders perform better at dimensionality reduction than their predecessor, principal component analysis, or PCA. Below is a comparison of two-letter codes for news stories of different topics, generated by both a deep autoencoder and a PCA. Labels were added to the picture for illustrative purposes. In the next video, we'll take a look at recursive neural tensor nets, or RNTNs.
Yeah. Anyway, let's have some coffee. Yeah, so Lee and Mariama, if you guys are bored with your project, right, you can use some autoencoders to project your news stories or whatever.